Hi, I'm Kenson, presenting TF-Coder, Program Synthesis for Tensor Manipulations. This is work done with David Bieber and Rishabh Singh at Google Brain. Coding in TensorFlow can be tricky. There's a huge API with about 500 tensor manipulating operations, and small errors can be really hard to find. The shapes and data types of the tensors are constantly changing as they're manipulated, and the TensorFlow operations impose constraints on arguments, such as type requirements and shape compatibility, and it can be hard to track down where exactly those constraints might be violated. So, users often ask questions on forums like Stack Overflow about TensorFlow, asking about some implementation help. We observe that these questions often contain a natural language description of what they want to do, as well as an input-output example demonstrating the desired tensor transformation. Inspired by this need, we built a program synthesis tool called TF-Coder that turns input-output examples into TensorFlow code solutions. The user first provides a specification of the task. For example, these input and output tensors demonstrate a task where we want to normalize the rows to have a sum of 1. The specification can also include an optional natural language description and any relevant scalar constants. TF-Coder then searches for a TensorFlow expression that satisfies the example. In this case, we can use tf.reduce_sum to compute the sums of the rows, and then add a dimension so that the division is done with broadcasting. This is a non-trivial problem with a solution composing 4 different operations, but TF-Coder can solve this in only 7 seconds. Now I want to show you a demo of using TF-Coder. This is actually a publicly available tool that you can use in Google Colab. I've connected to a runtime, and I've already run this cell to do the initial setup. Now, in this cell, we're going to provide the specification. So in this case, we have 2 input tensors called rows and columns, and we want to construct a matrix that contains all of their pairwise sums. So I can run this cell. And then the last step is to run this cell to invoke the program synthesizer. So the synthesizer is first going to print out the specification just for reference, and then it finds a solution where we are going to add the rows and columns in a broadcasted way. Now, it's not just toy problems that TF-Coder can solve. Actually, here are a bunch of real-life problems encountered by Googlers and users on Stack Overflow. And these are all problems that are pretty challenging because the programmers were seeking some help. But even so, TF-Coder can find solutions to all of these problems in only a few seconds. Now I want to give a high-level overview of how TF-Coder works. We start with the specification provided by the user, which is an input-output example, and optionally a natural language description and some relevant constants. Now, TF-Coder performs a search, where we keep track of all of the values we've seen so far. Initially, this is just the inputs and constants. In the search, we have a bunch of operations that we'd like to use, and we're going to repeatedly loop over these operations. For a given operation, we want to construct argument lists that are appropriate for the operation, where each argument is an element of the set of values that we've seen so far. Then we can apply the operation to the argument lists and save any new values that we find. We call this process bottom-up enumerative search. At some point, we might find a value that actually matches the output tensor, so we get a solution by recursively using the history of how we got to that value. And before the search begins, we can use machine learning models conditioned on the input-output example and the natural language description. These models predict operations that seem relevant for the task, and these predicted operations are then prioritized during the search. Now, here's the bottom-up search in a bit more detail, particularly in how the search is ordered. We enumerate programs in order of increasing weight. For now, we can think of the weight as the size of the program, but later we'll generalize this idea. Then, for each operation, we construct argument lists so that the resulting expression would have the desired weight. We run the operation on the argument lists, save any new values we find, and look out for solutions. We have three specific improvements over prior work. First, we use a weighted search to prioritize common or useful operations. Second, we use operation filtering to efficiently construct argument lists that satisfy all of an operation's preconditions. Third, we use machine learning models to predict operations relevant to the task, and then we can adjust their weights. Now let's look at each of these three improvements in more detail. So TF-Coder uses a weighted search. This is in contrast to previous work, which enumerates programs in order of increasing size, which is the number of nodes in the expression tree. However, if we only consider program size, then we're effectively treating each operation the same because they all contribute one node to the size. But we observe that operations can be very different. For example, the tf.expanddims operation is very simple. It just adds a new dimension to a tensor. It's very commonly used and useful in tons of situations. On the other hand, tf.reverse has more complex behavior and is only useful in more niche scenarios. Now, considering these differences, we would like to spend more of the search time exploring tf.expanddims compared to the amount of time that we spent on tf.reverse. We can achieve this by enumerating not by program size, but by program weight, which is a measure of the program's complexity. We manually assigned a weight to each operation based on its complexity and usefulness, where the simple and useful operations get smaller weights. Then we define an expression's weight to be the sum of the weights of the individual nodes. In this way, we can prioritize expressions that contain the simple, useful operations. There are a few key takeaways from this weighted search. First, an expression's weight measures its complexity, taking into account both the number of operations and how simple they are. And under this framing, the weighted search allows TF-Coder to find the simplest solutions first. Weighted search also allows TF-Coder to support well over 100 operations without much slowdown, because we can assign larger weights to the more niche operations so that they don't bog down the search. We'll see later that the weighted search enables machine learning models to adjust the operation weights depending on the task. And finally, because we assigned the initial weights by hand, we wanted to see how the synthesizer performance depends on our particular choices for the weights. We found that after randomly perturbing the weights by up to 25%, TF-Coder solves one fewer task out of 70 with a 6% slowdown, which is actually not that bad, considering that if we remove the weights completely, we have 10 fewer tasks solved. So it is very helpful to apply some human intuition in the form of these operation weights, but they don't need to be perfect in order to provide significant benefits. Now let's talk about operation filtering, which is used when we construct argument lists for an operation. First, we observe that TensorFlow operations require a lot of preconditions. tf.argmax requires that its first argument is a numeric tensor, so not a scalar and not a Boolean tensor. The second argument must be an integer that could be an axis, and in particular, it needs to be in range for the particular first argument. Some preconditions, like this last one, are about arguments being compatible with each other, which can depend on their shape, data type, or even the contents of the tensors themselves. And this can't be handled with simple type checking. We enforce these preconditions using argument filters and combination filters, which are predicate functions implemented in normal Python. The argument filters apply to individual arguments. So, for example, we can remove a Boolean tensor from being considered for the first argument to argmax. After we have a bunch of potential values for each argument, we can take a Cartesian product to get a bunch of argument lists. And then we apply a combination filter to check for the compatibility between those arguments. And in the end, we have argument lists satisfying all of the preconditions. Notice that operation filtering is broken down into two stages. First, the argument filters, and then the combination filter. We use the argument filters first so that we can avoid enormous Cartesian products. And then the combination filters enforce arbitrary preconditions in a way that is more general than simple type checking. Operation filters are also easy to use. They're implemented straightforwardly in Python, and the filter functions can be reused between operations and have their results cached for efficiency. Now, even though this idea is not actually too complicated, it's still extremely efficient. On average, these filters eliminate 98.6% of all potential argument lists for a single operation. And without operation filtering, TF-Coder solves 19 fewer tasks out of 70. Our third improvement is guiding the search with machine learning. We use multiple independent machine learning models to predict relevant operations for a task, and then we prioritize the predicted operations by reducing their weights. TF-Coder uses two machine learning models. One is a tensor features model that predicts operations from the features of the input-output example. We generate a synthetic training dataset using multiple bottom-up searches starting from random inputs. And we use the F1 score as our loss function, which balances precision and recall between the predicted operations. We also noticed that there's an imbalance in the frequency of operations in our synthetic dataset, so we scaled some loss terms to adjust for this. The other model predicts operations from the natural language task descriptions, using TF-IDF cosine similarity between the description and the TensorFlow documentation for each of the operations. These two models adjust the operation weights to fit a particular task, which then effectively reorders the search space so that likely solutions are considered sooner. In our setup, the models can be trained independently, which eliminates the need for a multimodal training dataset, which we don't actually have in our case. Our experiments show that these models are complementary, and together they lead to a 1.8 times speedup. For our experiments, we collected 70 benchmark tasks, 50 of them from Stack Overflow, and 20 that are encountered by Googlers. With a time limit of 5 minutes, TF-Coder solves 63 of the tasks using only 17 seconds on average. TF-Coder outperforms the prior work transit, which is essentially the bottom-up search without any of our 3 improvements. AutoPandas is a program synthesizer for similar sorts of data manipulation tasks using the Pandas library. And we found that TF-Coder actually outperforms AutoPandas on benchmarks from both projects, even though the Pandas tasks are harder to implement using TensorFlow. Here's an ablation study. The purple line is TF-Coder without the machine learning models. By adding the models, we get to the dashed green line with 2 more tasks solved. On the other hand, if we remove either the operation weights or the operation filtering, then the performance drops significantly. We also compared TF-Coder to human performance. Of the 50 tasks from Stack Overflow, we found that the Stack Overflow answers were correct for 32 problems, incorrect for 15, and the median answer posting time was 31 minutes. But TF-Coder performs significantly better on all of these metrics. We also compared to human volunteers on 6 new tasks, where the humans only succeeded in 50% of the attempts. On the other hand, we asked different volunteers to provide input-output examples for TF-Coder, which resulted in correct solutions 61% of the time, which actually improves to 94% after only 1 round of revision. Writing the example and then waiting for TF-Coder is also faster than the median time taken by humans. Now, TF-Coder is publicly available. Among usage data from the opted-in users, TF-Coder was used in over 500 sessions in about 60 countries, solving 509 unique problems, 71% of which in under 10 seconds. We also estimate that TF-Coder solves 84% of well-specified problems in the wild, which is just a bit lower than the 90% success rate on our 70 benchmark tasks. Now, I'm going to share a real story that demonstrates TF-Coder's practical effectiveness. This is a real task encountered by a Googler with lots of TensorFlow experience. Here we want to reorder some data in chunks according to these IDs. The Googler first solved the problem themselves. writing a 12-line function using 18 TensorFlow operations. They then discussed the problem with another Googler who came up with a different solution using 17 TensorFlow operations. So clearly this is a difficult problem. But then they used TF-Coder, which finds a one-line solution using 2 operations found in 2.5 seconds. And the Googler actually ended up replacing their handwritten solution with TF-Coder's solution, resulting in reduced code complexity and better efficiency. In conclusion, TF-Coder is a complete enumerative search using a combination of techniques that make it extremely efficient. We've seen that TF-Coder is competitive with human-level performance and can be practically useful. I want to point out that this was not obvious to us when we started this project. We did not expect a complete enumerative search within an exponential search space to be efficient enough to solve problems that humans struggled with, but it can. So perhaps the most important lesson to be learned from this work is that enumerative search can solve challenging real-world problems. Enumerative search can be surprisingly effective when optimized. You can check out TF-Coder at this link, and I'm happy to take questions. Thank you.
Thank you.
Okay, thanks for the great talk. 2 questions. The first question is regarding your comparison with auto-pandas. So if I understand correctly, it's not a strict like apple-to-apple comparison, right? In a sense that in auto-pandas, they didn't leverage natural language at all. So which means that in this case, when you win, so is that because of the actual information that you leverage in your framework, or is that because of your search algorithm, like fundamentally faster? That's one question. Mm-hmm. The second question is that how do you pick the benchmark from Stack Overflow? Because from our experience that like the distribution of the complexity of Stack Overflow is highly long tail in the sense that if you pick those like easy benchmark, and then if the way you're sampling the syntactic data is actually match the distribution of those long tail, you can solve those easy benchmark pretty easy. But there's a lot of long tail problem that is extremely complex, and yes, it's also very like difficult to solve. And how do you like extend your approach, or how is your current approach can solve that problem? Right. Thank you.
Mm-hmm. So the first question about the comparison to AutoPandas, it is not a perfect comparison because the Pandas library and TensorFlow libraries themselves are different with different functionalities provided. But we did our best to preserve the spirit of the problems as much as we could. There was a question in there about whether we used, let's say, natural language information. For the AutoPandas benchmark tasks, we did not use any natural language information, so just the numbers in the data frames. And then the other question about choosing tasks from Stack Overflow, we did actually make sure that the problems that we chose were reasonable, because what we did was we tried to solve these problems manually by hand. And if we couldn't solve them manually by hand, we threw it out. But we did include in the data set, in the 70 benchmark tasks, some problems that we currently know are actually too difficult to be solved with TF-Coder, because I think there are a few of them that to the best of our knowledge, the simplest solution contains like 10 or so operations. That's way too much currently, but they're still in our benchmark tasks. And I also want to point out that our results on the public data do show that TF-Coder is still really really effective, even for tasks kind of in the wild, what people would actually use.
Is there a quick question which might have a short answer? Then let's move on to the next speaker.